we have to find out what's actually going into our surface water. And the reason we want to monitor environmental pollution is we want to know just exactly what's going into it, because if we do know, then we can have supportable public and industrial policies that will be supported by the population at large. And again, the issue here is that we don't have that much time to do something. Within 100 years, water will probably cost more than oil. Part about pollutants all end up in our water supply. It doesn't matter whether they're put into the air or they're put in the soil originally, but rain will always bring them down into our water supply. And the reason we want to detect these pollution events is because we can contain them before they become part of the larger ecosystem. This is a schematic of generally how our water is supplied in our municipal water supplies. See, water goes from our reservoirs, goes through a sedimentation process which takes out most of the dirt, and then it goes through a filtration process where smaller particles are removed and the water is essentially clear. Then you add a disinfectant such as chlorine, and that kills most of the bacteria. Well, as you see from this diagram, everything that's intended here is to remove substances which are essentially visible. And there's a list of the things that you really don't want to know. In developing nations, 80% of all diseases that people contract are water-related. And you start looking at all of the things that reduce the water drinkability of the water supply, and the list starts getting very scary. 1 drop of oil can take 25 liters of water and make it unfit for drinking. There's a common herbicide called 2,4-D, and that 1 gram of that can contaminate 10 million liters of drinking water. PCBs, or polychlorinated biphenyls, which are very commonly, or were a very commonly used industrial product. 1 gram of a PCB can make 1 billion liters of water unsuitable for freshwater aquatic life. 1 gram of lead in 20,000 liters of water makes it unfit for drinking. And a lot of homes have lead plumbing, and lead plumbing was used extensively until just recently. And there's a cost to this that can be quantified. In the United States, it's assumed that 1 gram per million of lead per million gallons of drinking water reduces the intelligent quotient of children that drink that water by 1 point, which reduces the GDP, the gross domestic product, in the future by approximately $1 billion. And when we look at the way we treat water, approximately 99% of Swedes, 80% of Germans, 74% of Americans, 57% of Canadians, and everybody else somewhere further down the list are actually served by wastewater treatment plants that cleans up water that's been used for an industrial process or collected in wastewater. And we know for sure that continuing global industrialization will add larger quantities of active chemicals to the environment. And that filtration process that I showed you, here's what's not taken out. These are the things that will come through that process. And I know not all of us have had chemistry class lately, but you'll notice that there's a lot of chemicals on here that with some fairly strange names. Every one of these is produced by ordinary industrial processes, and every one of these can be found in drinking water at some point in the process. And we really do need to become cognizant that we have to monitor our freshwater feedstocks. And this is going to become a global issue over the next 20 years. And one of the things that has to happen is we have to develop new technology that will revolutionize the process so we can do real-time measurement of what's going in the environment. And the easy thing to do is to target those things that are easiest to get to at first. Easiest ones to do are hydrocarbon storage facilities, above ground and underground storage tanks, and wholesale and retail fuel depots. Chemical storage facilities, again, these are large above ground and underground tanks that store chemicals. Liquid hydrocarbon pipelines, which I know you've had some experience here in Brazil. And we generally need to monitor the constituents of the feed waters for all our public water supplies, and even more importantly, our underground aquifers, because the underground aquifers are refreshed on a century cycle. One of the things that we've been doing in this area is using fiber optic chemical sensors, which are a very significant technology advantage over the older methods of sensing species in water. And these things can be modified to sense many things other than hydrocarbons and the things that we saw on that earlier list. Currently using these things, these probes, to monitor above ground storage tanks. Again, there's a large number of these in the economy. They're there, but you don't see them because everyone ignores them after a while. But they are a source of a large amount of pollution of our groundwater and our surface water. And these tanks are very easily retrofitted with environmental monitoring equipment. And these technologies are very well understood and they're mature. The other significant source of groundwater pollution is underground storage tanks, such things as automobile fuel retailers, truck fuel retailers, private transport fuel depots, airports, and military installations, all of which use and store very large quantities of hydrocarbons. Again, the keynote here is that retrofitting these areas is simple and inexpensive. Now, if we start talking about pipeline leak detection, then we're starting to talk about a very technically difficult process and one that requires a very large-scale economic and technical commitment. But it's worthwhile doing because catastrophic failures of pipeline lead to significant changes in the public perceptions of the pipeline industry and the energy industry and the government that regulates those industries. Here's one of the things that people don't talk about: the possibility of chemical and biological attacks on the water supply. And public water supplies are just uniquely susceptible to terrorist attacks because they're not guarded. No one guards water because it's not valuable yet. But you can be assured that a large-scale, coordinated, technically advanced attack can devastate the economy of an entire country. It hasn't happened yet, but it will happen at some point in the future. One of the leading proponents of water quality monitoring is the government of the Netherlands, and they've got a large-scale project where 17,000 wells have been dug in various areas of the country. They monitor the water that goes through their waterways and through their wastewater is put back into the waterways and the deep water aquifers. They've been doing this with small electronic modules that can be submerged deep in a well. And these modules sense certain things such as salinity, pH, and a few simple chemicals. Then the modules are manually pulled to the surface and the data gathered once a month manually on a laptop computer. They also have small electronic monitors that are submerged deep in aquifers. These are 300 meters to 400 meters deep and does the same process. And again, in the case of the Netherlands, the reason they've done this is because the port of Rotterdam was probably the largest concentration of hydrocarbons and chemical refining activity in the world. And over the years, the spillage that's resulted from it has caused a substantial amount of pollution to their groundwater and their deep water aquifers. The existing sensors that we've been working on start off with the BTEX, which is a nice way of contracting benzene, toluene, ethylbenzene, and xylene, all of which are signature products that are in automotive motor fuels. Also ethanol and styrene, and I know you have a lot of ethanol and gasoline in Brazil, so this is another one of those components that's a signature. When you find this in place, you know you've had a leak somewhere. And the next generation of monitoring equipment is going to be much smaller, cheaper, and more sensitive. The sensitivity will go from parts per million that it is now to parts per billion. When you reach the parts per billion level, then you can start making quantitative decisions about what you're going to do with your water supply. And these devices will eventually be linked to databases at government agencies and industry over terrestrial and satellite wireless networks. And the reason they'll do that is because the infrastructure, the area that you need to cover is so large that you can't put in terrestrial wireline infrastructure. It has to be wireless. And the data that's generated by these sensors will be available over the internet to a variety of clients, including government regulators and the industry members that support these efforts. Here's a chart of a raw data that's taken from a fiber optic chemical probes, a set of probes that's installed underneath an above ground storage tank in Florida. This is used for experts, obviously. You have to know what all of these numbers mean. When you talk about internet delivery, you can put this information into a much simpler form, and it can be processed by non-technical people. And this is the true power of it. You can take large amounts of data, and you can reduce it to easily understandable charts and graphs. The next generation of sensors we'll be working on are ones that detect pesticides. This is because agricultural pollution is an ever-increasing problem. Neurotoxin, because, again, terrorist attacks will occur at some point, and there is a demand for products like this. Heavy metals, sensing lead and chrome, which are probably the two most pervasive heavy metals in the environment. TCE, which is trichloroethylene, which is a very common industrial solvent. Unfortunately, you start finding high concentrations of TCE in deep water aquifers, deep ground aquifers. You can find these things 1,000 meters down in fresh water, and once they're in there, they'll never come out. And PCBs, again, it's a commonly used industrial chemical. Essentially, these things will all be reduced to the microchip size. Now, the reason you want to get it to a chip size is because now you can manufacture very large quantities of sensors at very low cost, and you can put them out in areas where you wouldn't ordinarily be able to put what's essentially a chemistry lab. Now, when everybody goes back to work on Monday, you'll be able to use some buzzwords that I give you here. These are single source, dual beam spectrophotometers. So there'll be a short test after this. Where we're really going with this is what we call sensor fusion. And in that case, we're taking small wireless communications devices, and we're putting these chip sensors on these communications devices. And the reason we're doing that is to reduce the cost and decrease the power consumption. And once we've reduced the cost and decreased the power consumption, we can make small battery-powered units that we can put out on a large scale without requiring any investment in terrestrial infrastructure. And that way, we can actually get to the point we can enable the monitoring of water supply feedstocks on a national basis. So without the ability to reduce the cost of these devices dramatically, no one's going to put them out on the scale that's required. But if they are reduced in cost, and they can be remotely mounted, then it does make sense to do it. And does anybody have any questions? Thank you very much.
You can give an idea how work a sensor like this to recognize an appearance, one part in an appearance?
Well, the technology is fairly well understood. It's called index of refraction, and you make a cut. The most sensitive way to do it and the cheapest way to do it is using a phenomenon called index of refraction. You change the chemical surface of glass and you shine light through it, and that chemical surface that you put on the glass is sensitive to whatever you're trying to measure. And when what you're trying to measure bonds to the glass, it changes the amount of light that goes through the glass. So you can just see the correlation of light intensity versus concentration.
For the water in the apartment. At minimum per apartment, maybe $50 amount. It's too much for a water, okay?
It's probably going to be a lot more than that in 100 years.
You believe that we can use this kind of sensor in every home? Is cheap enough to use it? Or this is more a high-level system, a region, and not for home?
It's a high-level system because once you've got the water that you're going to use into your water treatment system, then it's too late. You have to know what's going into your water treatment plant before it gets there. So the idea is to contain the pollution before it ever reaches the water processing.
And how you can recognize in your home, in your apartment, in your small village that the water is good?
Well, on the village level, you could do it by looking
small
at
village.
Yeah, you could do it on the input or the main pipe that supplies water to the village. You would put the sensors there, so you would have a communal monitoring system.
Peter, can we talk a little bit about what you're going to do with the signal from the sensor?
Yes, generally the sensor itself is a very intelligent device, and again, it's part of the communications system itself. Every communicator, every wireless communicator has a controller on it that has all of the intelligence for the device. That controller is used to read the sensor and to transmit it, in our case by satellite, over to our main server, and from the server then we deliver the data to the customer over the internet.
Okay, thank you.
Yes, sir.
Peter, when are you going to be having the cheaper model in the market? Do you already have it?
No, we have the components. The devices themselves are probably 6 months away from very large-scale deployment. The sensors themselves exist. It's the process of integrating the sensors into the communications, but that's ongoing now.
Okay, I completed the question of my friend there. To measure the quality of our water, there are some places in Rio where you still extract the water from the ground. Okay, are these ships going to be good enough for we to measure, normal people, to measure the quality of these underground water?
Potentially, yes. They're cheap enough you could potentially do it, but generally you wouldn't want to do it that. You'd want to do it in the distribution system.
But there's no distribution in this case. Which house make
Oh, I
a
see.
hole in the ground?
Individual wells?
Individual well, that's it.
You could. The question is whether it be economic or not.
I see, but it's that easy to measure the signal? Which have a laptop or notebook and measure the signal and collect the results?
You could, yes. Frankly, no one's ever asked to do that before, but yes, it could be done.
Okay, hope so. Thank you.
Peter, I just would like to make a question also, Peter. In Brazil, we just faced a series of leakage in oil pipelines, and you know that caused a big environmental damage. How do you see this technology helping preventing that? You know, something that does not help a lot if we monitor the ground or the environment, and we know that there is a huge damage made. We want to understand better how can we prevent that? How can you use this technology to prevent leakages?
That's a great question. Generally, all catastrophic failures are preceded by small leakages, and those leakages grow over time until finally you have total failure or large enough leakage that someone can see it. You want to stop those before you get to that point. So the sensitivity of the sensing device and the fact that you can mount these things remotely over the entire length of a pipeline is really crucial. If you know that 1,000 kilometers of pipeline, say every 10 meters, you know that you have nothing in the soil at every 10-meter spot, then you can be fairly certain that when you do have a small leak, it doesn't take very long for a small leak to reach, say, the 5-meter range, which is your worst possible case. Well, 5 meters of pollution from a high-pressure pipeline is a very simple occurrence. It happens a lot, and it's easy to detect. So if you can detect these things before they become catastrophic failures, then your remediation process or your cleanup process is reduced to, say, 5 or 10 meters of soil versus just multiple cubic meters, just thousands of cubic meters of soil, and the environmental damage that goes along with a major catastrophic spill.
Peter, can you explain how the information goes from the sensor to the final user, and how easy to use is the information that we have? I mean, in how is the internet and everything else built into the system?
Well, the sensor itself is part of the communications network. In our case, it's part of an Iridium communicator. And the sensor reports to the satellite. The satellite downlinks the information to a server. And from that server, it's automatically available on the internet to anyone that's authorized to use the information. So it's really a seamless process of getting from the sensor to the internet. As far as the user is concerned, it looks as if the sensor itself was actually on the internet, even though it's not really.